my name is Feshte. I just started my second year postdoc with Kelsey Thomas. And thanks for the opportunity to present some of my research interests and work and what I want to do with it in the future. So overall, my research interests are better understanding symptoms of disease and disorders, and specifically what networks underlie these symptoms so that we can then maybe target them in the future. So that's the overarching research interest of mine. I'm going to start with my background and some of the questions that I have. And then I'll go into my current research projects, the one specifically sponsored or funded by the REC Scholar Program, and then where I'd like to take this work moving forward. Okay. But before science, here's my research journey geographically. So I'm from Orange County. I'm from Anaheim. So I studied at UC Irvine. As an undergrad, I majored in psychology, cognitive science. And then after graduation, I actually worked at a clinical trial site for a couple of years as like a phase 3 medication trials. So I worked a lot with patients from neurology and psychiatry. It was really cool to see the translational side of research. And that was also where I met neuropsychologists for the first time. I was like, that's cool because I like the brain and I liked working with patients. So I was like, I want to do what they're doing. And they were like, great, go to grad school. So I was like, okay. So I applied to grad school and they're like, no, get more research experience. And I was like, okay. So I went back to UC Irvine for post-bac research experience in an academic setting where I worked with Dr. Steve Kramer in his neuro rehab lab. And then I also worked with Dr. Joseph Wu at the Imaging Center, where I was like an analyst doing neuroimaging analytics. And this is really where I learned about imaging technologies like EEG, MRI, DTI, and how we can use those to better understand like neural injury or identify neural injury early. At the time, I was using EEG to study stroke. Okay, and I was like, this is it. I like this. So I am going to apply again. And I did. And then I went to Philly for grad school in clinical psychology, where I specialized in neuropsychology at Drexel University. Here I worked across 2 labs. I was their first, they started calling us crossover students, which meant that my primary mentor was in the neuroscience program with John Medaglia. Then I was also co-mentored by Maria Schultheis in the clinical program. So I had best of both worlds there. This is really where I began building a research program around applying neuroscience models and frameworks to understand cognition and symptoms within progressive diseases. So John, his lab was using a lot of network science tools, which is what I'm going to get into and why and how I see this being applied in aging work. And then Maria was more like ecological validity and functional, like studying functional behaviors. And then my specific focus was on studying fatigue in multiple sclerosis. So I studied it behaviorally, and then I also studied it neurally. And I was specifically interested in the frontostriatal circuit and how that related to fatigue and how fatigue emerged in individuals with MS. And I deleted those slides from here, but if you guys want to ask me about fatigue, I know all about it. Okay, so the last year of my program was my clinical internship up at the VA Boston. I went more north and more east. For some reason, I thought it was closer to California, but I am geographically challenged. So it got colder. And at the VA, I majored in neuropsychology and I minored in geropsychology. And what this started to do for me was working with these older adult patients, my population interest started to shift. So I've always been symptom focused, but then I became more interested in neurodegenerative disease processes and how and what symptoms emerge in these processes. So I was like, okay, I want to do aging research. Will someone take me? And Kelsey Thomas at UC San Diego did. So that brings me to now I'm back closer to home at UC San Diego working with Kelsey Thomas and Katie Bangan. And on my postdoc, I've been taking my symptom approach, specifically neuropsychiatric symptoms has been my current focus, and applying it to another type of progressive disease. In this case, it's aging or progressive process, aging and neurodegenerative diseases. So I started here, I went east and I came back. I learned that you don't wear an Eagles shirt in Boston in public at all. not even the grocery store. I also learned that I have zero fan loyalty. Like I get peer pressured into being on anyone's sports team very easily. Okay, so my research has been motivated by this bridge between neuroscience and neuropsychology. Neuropsych gives us this really rich behavioral, cognitive symptoms, patterns of performance, like information. We get really good functional information over time, good lived experience. And neuroscience tools allow us to really understand the mechanisms that drive what we see in neuropsychology. So we can draw from systems neuroscience, network theory, neuroimaging. And my goal is to continue working on this bridge. So with my current research interest not being in only describing symptoms, but also asking what's happening in the brain that gives rise to the symptoms that we see. Okay, so my current goals are in identifying symptoms that may be these early modifiable signals of risk, and in figuring out how we can intervene before irreversible decline sets in, or if there's a way for us to reverse any sort of decline we see. Why study symptoms? There are many ways to study disease: biomarkers, imaging, genetics, cognitive testing. If we're a car, and I think in analogies, so a car is one of them, and I really hope you guys watched Wicked because that's like a big analogy in the future. And anyway, all right. So if we're a car, biomarkers are like the diagnostic computer that the mechanic uses. Neuroimaging is like taking a look under the hood. Genetics tells us about the car's factory settings, models, specs, things we can't change, but it gives us a sense of how the car is running. And then cognitive testing, as neuropsychologists, we're like test driving the car. We can see how fast it accelerates, how it responds to sudden turns, gives us good functional information, especially over time. And then symptoms are like the check engine light. I like to think of them as the check engine light. And I found myself drawn to symptoms because they're often the first thing to show up. They're the thing that patients often notice early on, whether cognitive or psychological or behavioral. They emerge before the formal diagnosis. It affects everyday functioning. They're also potentially modifiable. So I'm a symptom stan. So the questions that drive my work are: what brain regions and their networks underlie these symptoms? How are symptoms in these circuits related to neurodegenerative disease processes? Can we use symptoms to identify who's at risk even before cognitive impairment? And ultimately, can we target and modify these symptoms to slow or prevent decline? Okay, so I haven't been an aging researcher long, but I've always seen this graph in talks. I was very excited to put this up here for mine. So when it comes to Alzheimer's disease and related dementias, we know they progress over many years with changes in amyloid and tau long before dementia is diagnosed. Now, early detection work focuses heavily on biomarkers and cognitive testing or cognition. For example, much of the Nova Labs work has focused on the earliest detectable cognitive changes. So when I first started, this is what I kind of jumped into. So this little like oval on this graph here. In recent work, when I started in the lab, Dr. Thomas and our wonderful grad student, Caitlin, have been using these data-driven approaches using neuropsych test data from the Baltimore Longitudinal Study of Aging, examining the heterogeneity of cognitive performance within cognitively unimpaired individuals to determine if there are specific phenotypes or these groups that might emerge that have increased risk of developing MCI or dementia. And what we found on the left, you can see like the results of the latent profile analysis we ran. So you can see that these different cognitive profiles have emerged from performance across multiple neuropsych tests, and each line represents a different phenotype. So this red group is this like low average, this executive group. And then we have these green and olive groups that are pretty similar, except they differ in terms of memory. One does better on memory, one a little worse. Then this blue group that's a little higher performing, but they have worse memory. And then this purple group that's high all across the board. And even within this cognitively unimpaired sample, we see meaningful variability with these groups. And then when we follow these individuals over time, shown on the plot on the right, we see that these phenotypes have different trajectories of progression. So this red group, this low average, this executive group decline the fastest with higher risk of progression to MCI dementia, followed by the average low memory group. In ERIC, apply this similar approach. which is the atherosclerosis risk in community study. Again, we're finding these subtle cognitive phenotypes that have unique biomarker profiles and different rates of decline. So for example, this low overall, very low memory blue group, and then this pink group, which is the subtle low overall, low executive group, demonstrated elevated risks of dementia progression. So when we're looking at cognition, this tells us that not all cognitively unimpaired individuals are the same, and that these early cognitive profiles could be a useful way to stratify risk and guide earlier intervention. So that made me wonder whether we could examine neuropsychiatric symptoms in the same way. And this led to my REC Scholar program project proposal. So neuropsychiatric symptoms are being increasingly recognized as these early clinically meaningful indicators of ADRD risk. They encompass a range of behavioral and psychological changes like anxiety, aggression, agitation, depression, sleep disturbances. And just like cognition, they vary widely in their presentation. Now, typically, the focus has been on the severity of these symptoms, or there are studies that examine specific neuropsychiatric symptoms like agitation is very popular, and how they relate to risk. But because symptoms don't usually happen in isolation, I was interested in how patterns of neuropsychiatric symptoms might be emerging. And the MBI, the Mild Behavioral Impairment Checklist, is something recently implemented. It's like this questionnaire that has structured symptoms into 5 predefined domains. And so this is like this theory and consensus-driven looking at patterns of psychiatric symptoms. But I was interested in taking the same data-driven approach we've done with cognition and applying it to neuropsychiatric symptoms. So do we get these natural groupings of symptoms or these like distinct profiles that are associated with differential patterns of ADRD risk? So that was my question, what I wanted to examine. Okay, so my study, my REC Scholar study, used latent class analysis on over 20,000 cognitively unimpaired older adults from the NAC dataset. And neuropsychiatric symptoms were identified using the NPI-Q and the geriatric depression scale and entered into the LCA. So my first objective was to see, are we getting different profiles from these like different symptoms that we're putting in? And we did. So the LCA identified 4 distinct neuropsychiatric symptom profiles. There was this low all group, or just low endorsement of symptoms across the board in purple. And then this like high depression group is what I called them in like the reddish color. And then this high agitation, anxiety, irritability group in this blue, and then a high all group where there was endorsement of symptoms across the board. And these profiles weren't just statistically different, but they also differed in terms of risk to dementia MCI. And so I wanted to examine, well, spoiler alert, they did, but I also wanted to examine whether there were differences in rates of progression to MCI dementia. And then I also wanted to look at cognition over time. So that's what's coming up next. But before that, demographics. So the majority of participants fell into the low all group. It was about 70%. This is still pretty like, they're not endorsing many symptoms. But then we did have other portions in high depression at 17%, high agitation, anxiety, irritability at around 9% of the sample, and the high all group was about 3% of the sample. Mean age was about 70. And then those in the high all group tended to be slightly younger, and women were more represented in the low all high depression groups. So there were 20,599 cognitively unimpaired participants put into the LCA to get these profiles. And we had about 15,400 who we had follow-up data on that I was able to look at cognition over time too. And then like whether they converted to MCI dementia. And then there was 15% of that sample who progressed to MCI dementia over follow-up. Oh, whoops, here are the profiles again. Okay, so when we fit a Cox proportional hazards model to examine progression to combined designation of MCI dementia, we found that the high all group showed the highest rates of progression, followed by the high agitation, anxiety, irritability group. So it was about 2.5 times for the high all group and 1.8 times higher risk of progression for the high agitation, anxiety, irritability group. And then if you're interested, high depression was about 1.2 times. And then for cognitive outcomes, we used, so on the right, you'll see a plot for baseline cognitive differences. It's pretty small, but the top is baseline cognitive differences, and then the bottom is like over time. And basically, the high all group had lower baseline and faster decline across all the domains. But other than the high all group, the high agitation, anxiety, irritability had lower baseline for memory and didn't show any practice effects over time. The attention group had the high depression group had lower attention and faster decline. And then the same for executive functioning. Okay, so we have some evidence that there are these patterns of neuropsychiatric symptoms that emerge in these cognitively unimpaired older adults, and that they do differ in terms of risk of progression and cognitive trajectories. And there are imaging studies to suggest that prefrontal, cingulate, and limbic systems are associated with individual symptoms, but we don't know which symptom patterns or patterns of symptoms are tied to brain network changes in a way that might signal early disease. So for example, this is like the theory I'm working off of. I don't know if this is true, but this is what I'm thinking. Possible that network changes might be arising due to underlying pathology that happens early in a disease process. And that type of disruption that occurs is what's driving the expression of certain symptoms. So and specifically these patterns of symptoms. So like pathology happens, it disrupts this network, and then we see these symptom patterns emerge. So next steps in my interests are in studying what these network changes might be that are associated with neuropsychiatric symptoms. And I want to do that by applying network neuroscience approaches, like using network neuroscience to study this. Okay, so I want to get into network neuroscience, and I usually lose myself in this, so I apologize if I lose you. I'll try not to. Please ask questions. Okay, so network neuroscience is a framework that models the brain as a system of nodes and edges. It's essentially putting a graph onto a brain. It lets us move from asking what's active to how systems work and what happens when it breaks down. So here, each node is a brain region. So there are 3 up here. And each edge is a structural or a functional connection. And edges are just the connections between the brain regions. And this image on the right is what captures the core idea behind network science and control theory specifically. So you have this anatomical brain image showing the location of key brain regions or nodes. And then if you're interested, for example, in the structural connections, you would put in an MRI tractography showing white matter connectivity. And then using both of this information, you create this connectivity matrix and tells us which brain regions are connected and how strongly. And then from there, you can then derive this abstract network model, which is what you see on this far right, where we can start to simulate how activity flows throughout the brain of the network or how control might be exerted. Okay, so the blue arrows, for example, and the waveforms above them here illustrate what happens when control signal is being applied. So activating one node sends signals through the network, which can shift the brain from one state to another. So we can then examine these properties. So once we model the brain as a network, as this graph of nodes and edges, we can start to then examine its properties or like characteristics that tell us something about how the system is organized and how different regions influence each other. And the 2 properties that I focus on are, I'm going to show a lot of graphs, but I'll go through them with my wicked examples. So centrality tells us which regions are most important for keeping the system connected. You can think of it as like how the brain is organized, how the regions are organized within the brain. It's like more structural. Well, no, it can be both structural or functional. It's just think of it as organization of the brain. And then controllability is about influence, so how regions influence each other. Okay, so we'll start with centrality. So the 3 metrics of centrality that I'm interested in are degree, betweenness, and eigenvector. So degree of centrality measures the importance of a region based on the number of direct connections. Someone with high degree of centrality, you can think of as like someone who has a lot of connections, like Glinda and Wicked, who's very popular and has a lot of connections with other people, like right. So it's a brain region that has a lot of direct connection. Betweenness centrality measures the importance on how often it lies on the shortest path. So you can think of betweenness centrality as like if you have high, like someone who gossips a lot has high betweenness centrality. If you want information to spread quickly, you go to that person because like they're going to spread that information quickly. So it's like gossip. And then eigenvector centrality measures a brain region's influence in a network. And so it's a region that's connected to other highly connected regions. So I use Glinda again here as an example because she is well connected to Madame Morrible, who's like a powerful player. And then she's also connected to Alphaba, who's also a powerful player. So it's like a region that is well connected to other well-connected regions. You know, think of friends with powerful players. Okay, so that's centrality, and it's more about like organization of the network. And then we have controllability, which looks at influence, like how influential a node or a region is. So there's average controllability, which is the ability of a region to steer symptoms into nearby or easy to reach states. So it's good for identifying regions that stabilize short-term symptoms. You can think of like low energy brain states. And again, I use Glinda because I'm bad at coming up with examples where she's good at influencing like her friend group, right? She is able to take them from like hating on Alphaba to like them liking her. Like, so it's like she's easily influential within her own friend group. Whereas modal controllability, you can think of as Alphaba. So like a brain region with high modal controllability is able to push the brain system into difficult to reach states. And this is a brain state that's like far removed. It's not well integrated within a network, but it has a lot of influence. So commonly in the brain, like the dorsal anterior cingulate cortex, the DLPFC, the inferior frontal gyrus, these are examples of regions that have high modal controllability because we can, we go from rest to being able to switch back and forth or hold information in mind versus like the default mode network would have high average controllability. It's able to take us from like mind wandering to light focus, for example. So these are like the two different controllability metrics that I'm interested in. Okay. So I've said all that because I think that we can use network measures to understand. I think it's important to use, well, no, I want to apply and use network measures to understand the brain and brain changes that underlie symptoms. There haven't been many studies that apply these measures to aging and ADRD. And those that do show age-related reductions in network degree, for example, so number of connections and how easily information is transferred, particularly within frontal, parietal, and temporal regions. These reductions are also shown to mediate different cognitive functions like attention and executive functioning. Now, there are some studies that also show increased degree centrality in, for example, the middle frontal gyrus, even though there might be atrophy there. So and I think that's notable because even in the presence of local atrophy in these regions, increased centrality within the network has been associated with better cognitive performance. So, I think it highlights the value of network measures which can capture like compensatory mechanisms and meaningful differences that aren't detectable through like atrophy alone. And then outside of aging, network theory has already been applied in areas like language and aphasia. There are studies that show that controllability metrics identify influential regions in recovery, and that the type of controllability within certain nodes or regions is correlated with better outcomes. And we can use this for targeted intervention. So TMS studies, for example, that target these high controllability regions, so high modal controllability in the left inferior frontal gyrus, when targeted, has led to increased word generation in a TMS study in individuals with aphasia, in stroke patients with aphasia. So in thinking ahead, I'm interested in using these metrics and being able to identify the regions underlying clinically important symptom patterns because they can then become targets for TMS in the future, I think. Okay. So I'm just going to give an example here of like what I would hypothesize. So if we have these different neuropsychiatric symptom profiles, for example, these might be the different centrality and controllability measures we find associated with it. So in high agitation irritability, if I'm looking at the network, we might find higher degree or more connections, which may reflect heightened input from limbic or sensory regions, which would then maybe lead or explain hyperresponsivity to internal or external stimuli, which could then make the system overreactive to minor emotional cues. We might also see, excuse me, high modal controllability within limbic regions, which might lead to an individual jumping from rest into high arousal reactive states too easily or too quickly. And then this might be a target for TMS to help decrease modal controllability and then maybe decrease like the high reactivity or responsivity or, reduce agitation or irritability. So this is like down the line what I'm thinking what I'd like to do or study with this work. Okay. So repeating myself a little bit, but thanks to the Rec Scholar program here, we've been able to identify these potentially higher risk profiles within one cohort, and I want to expand that into different cohorts. And also what we don't yet understand is why certain symptom profiles might confer greater risk or what brain mechanisms underlie that vulnerability, which is, again, what I'm focused in and interested in studying. So identifying, characterizing these naturally occurring symptom patterns rather than relying on total scores or predefined domains, or seeing how they complement predefined domains like with MBI. Something I want to do, and then testing whether certain profiles align with specific patterns of structural network disruption. Down the line, we could look at functional network disruption, and then determining whether this like pipeline between pathology, network change, and symptom expression is a plausible mechanistic pathway. Okay, and so potential impact of this is we'd be able to define clinically meaningful profiles in preclinical ADRD, identifying the neural mechanisms that link these symptoms to ADRD pathology, and then using that knowledge to guide earlier targeted prevention strategies. All right, so bring it all together. My work is driven by the idea that symptoms are these meaningful signals, early observable indicators of underlying brain system changes. I want to know what are these brain system changes, if there are any, but I'm guessing that there are. And then through this lens, I'm building toward a framework that uses network science to understand these symptoms within the neurodegenerative process. And then the goal is to eventually be able to predict and then intervene on the pathway leading to cognitive and functional decline. So by integrating behavioral, clinical, and systems neuroscience approaches, my long-term goal is to develop the circuit-based model of risk that can inform earlier detection and then prevention down the line. Okay. Thanks so much.